Hi, so today we're going to talk about gas laws. And this video hopefully will be just a short overview of the different gas laws you're going to encounter. And then I will likely make another video with more examples, but just to give you a quick idea of what the gas laws are, then you can go and start to practice using them. I'll make another video where I go through and do examples with you. So first, overall relationships. So we have some variables that we're going to talk about with gases. We have pressure, we have volume, we have amount, and we have temperature. And so thinking about what each of these are, pressure is based on the particles pushing against the walls of the container. So your tire pressure, for example, in your bike or your vehicle is the particles of gas inside of your tire pushing against the walls of the container. And you can measure that with measuring devices. Volume is the amount of space the particles take up. If you get into upper level chemistries, you'll realize that in this class, we assume that the volume of the container is the same as the volume of the space the particles take up. So if you fill up your tires with gas, with air, then the volume that the particles take up is the same as the volume of the interior of your tire. That is an assumption that we make in introductory chemistry that will be talked about when you get into upper level chemistries. That's not always the case, and we'll have to adjust for that. The N is going to be the amount of particles, which I believe is pretty self-explanatory, and the temperature of those particles. Now, temperature is a measurement of the average kinetic energy of the particles. And here we're talking about gas particles, but temperature is the average kinetic energy of any particles, including solids, liquids, or gases. So these are the variables we're going to be looking at. How much do the particles push against the walls of the container? That's pressure. What is the space the particles are taking up? That's volume. What's the amount of particles we have in there? That is going to be N. And then the temperature is the average kinetic energy of the particles. Now, when we're talking about units, let's briefly talk about units. Pressure units are going to be atmospheres, or ATM. Millimeters of mercury. You can also have inches of mercury. Oops. Inches of mercury. You can have PSI. Maybe you're familiar with some of these. There's also other units like pascals, kilopascals. Bar is a pressure unit. You're going to be focusing on ATM, millimeters of mercury, and then torr is the same as millimeters of mercury. I will give you any conversions you need to convert between these. So you don't have to worry about memorizing any conversions between these different units. You will be given the conversion factors for these, but you will have to sometimes convert between different pressure units. There are a lot of pressure units because a lot of people have studied pressure, and different pressure units come from different ways of measuring. For example, take a quick look at the atmospheric pressure. Just Google weather.com atmospheric pressure, and you'll probably see millimeters of mercury or inches of mercury because they put mercury in the barometer, and how many millimeters or inches the mercury moves in the barometer, like a thermometer kind of, but it moves up and down. That's how they measure it. So that's exactly where that comes from. You're familiar with volume already. We have milliliters, liters, gallons, any liter-based unit, ounce, any length cubed based unit. So here are some different length cubed based units: miles, inches, meters, centimeters cubed. And I'm just going to put etc. for both of these because there are more, but these are just some examples. N is moles. Moles only. Technically, you can measure amount in grams. So if you're given grams, convert to moles. You can use the conversion called molar mass to go from grams to moles. So if I tell you, hey, I put this many grams of gas in something, then you're going to want to convert it to moles before you do any of these gas laws. Lastly, we have temperature, which always has to be in Kelvin. So if you're given degrees C or degrees F, you have to convert to Kelvin. Because Kelvin is on an absolute scale. And when you look at the formulas I'm going to show you later, you'll realize that we cannot put anything 0 on the bottom of a fraction. So that rules out Celsius and Fahrenheit as options for temperature. And so, for example, 0 Kelvin is absolute 0, and we don't really work in absolute 0. Even space is like 2 or 3 Kelvin. So we don't really need to worry about absolute 0 on conditions here on Earth. Even if you're working in space, you're at least 2 to 3 Kelvin. So you do need to convert to Kelvin there. So moles and Kelvin are units that must be used anytime we're talking about gas laws. But pressure and volume, you can use any unit as long as they match up and cancel out when you're doing your math. So you do have to be aware of them, but they can be any unit that you need them to be. Let's look at some relationships. Pressure and volume. I want you to think about a balloon. Okay. Now let's hold everything else constant. Temperature is not changing. The amount of gas inside the balloon is not changing. If I squeeze the balloon, if I apply an increase in pressure, and squeeze the balloon, what happens to its size? If I squeeze the balloon in, it's going to shrink in size, right? So we're going to lower the volume. So pressure is directly proportional to the opposite of volume because they are indirectly proportional. Or inversely proportional. This symbol is a proportionality. So pressure is proportional to the opposite of volume. So we put volume on the bottom here. But what you need to go is if pressure goes up, volume goes down. right? They're opposite. If pressure goes down, volume goes up. If I release the balloon, if I go backwards and release the balloon, the volume will increase. So higher pressure, smaller space. Lower pressure, bigger space. So that's one relationship. Another relationship is pressure and temperature. So let's grab my balloon again. And this time I'm going to increase the temperature. Oh wait, I don't want to use a balloon because actually a balloon will not work here in this situation because balloons can change their volume. So let's think about your tires. Okay, so your tires, I'm trying to draw a tire. Here we go. So your car tires, give myself a little wheel here, or bike tires. If you increase the temperature and you drive around, the particles inside are going to heat up. When they heat up, they move faster because temperature is a measure of kinetic energy. So particles move faster. So the pressure is how the particles are bumping into the walls of the container inside the container. Okay. If the particles are moving faster, they're now going to hit the walls of the container more. So we're going to increase the amount of movement we have inside here. And that's going to mean that it's going to hit the walls of the container more often. They're bouncing around more often. So that's going to be higher pressure. So higher pressure. If you increase the temperature, and if you want to do this, try this. Next time you get in the car to drive, before you get going, if you have a way to measure your tire pressure, measure your tire pressure, write down what number it is, drive for a little while, get out and measure it again. It will be higher after you drive for a little while. So pressure goes up and temperature goes up. So pressure is directly proportional to temperature. So P and T are directly proportional. Directly means that one goes up, the other goes up. You see, I'm basing this all on pressure because that is easiest for our general understanding. It is not necessarily the way that all of the gas laws are built, but I believe that it's easier for most students to grasp. You can do these relationships, like you can do a temperature volume relationship and a volume moles relationship. Those are different gas laws, individual gas laws. But I think just for our understanding of where the gas laws come from, just relating everything back to pressure, holding everything else constant. So when we talk about pressure and volume, temperature and moles are the same. If we talk about pressure and temperature, the volume of your tire is the same and the amount of gas in your tire is the same. Let's talk about pressure and moles now. Actually, let's talk about volume and moles because let me stick to at least one gas law here. Volume and moles would be easier to talk about because we can talk about balloons here. So with balloons, they actually keep the pressure of inside the balloon and the pressure outside the balloon always stays the same. So we don't have to, when you're just blowing up a balloon or just have a balloon. Now, when we're doing this trick up here where we are squishing the balloon, that's a little bit different. But if the balloon is left to do its own thing, the pressure inside and outside is going to stay the same. So if I have my balloon and it has some moles of gas in it, so I'm just going to use some little dots to represent the particles. Got some particles of gas in it. If we increase the amount of gas in there by blowing into the balloon, what's going to happen to the size of the balloon? It's going to get bigger, right? So I'll put in some dots. That was the before dots, and I'm going to put in some red dots. These are the extra ones we blew in there. So now we have more moles, and the balloon expanded to give us more space for that. This is assuming that the pressure inside and outside is staying the same. If it's a closed container, let's look at that really quickly. Pressure and N. If it's a closed container, like your tire, if you put more air in your tire is not going to get bigger. It's not going to increase in volume. It can a little bit increase in volume. You maybe see that a flat tire looks a little different, but what you're going to be actually measuring is the pressure, right? So lower pressure, higher pressure. So you can measure that. Put more gas, put more air into your tires, and then read the pressure. It's going to be higher, right? Because we're assuming the tire is not leaking gas all the time. It's not like an open container. So both of these relationships are direct. So pressure in moles, volume in moles are directly proportional. So that means we can say pressure is directly proportional to N and volume is directly proportional to N. Now let's take a look at all of these relationships and look at them together. First, we have pressure is directly proportional to the opposite of volume. Then we have pressure is directly proportional to temperature. Then we have pressure is directly proportional to N. And then we also have volume directly proportional to N. Now, if I were to just kind of put all these together, I would get pressure is directly proportional to N and T, but inverse to volume. I hope that makes sense what I just did. So I'm just kind of combining things. It's directly across from T, directly across from T, directly across from N, directly across from N, but one directly across from 1 over V. So we have to put V on the bottom of the other side. Now, when we're doing math, proportionalities are fun to think about, but I can't actually plug in and get any values out with proportionality. So what we do is we add a proportionality constant. And someone did a lot of work to figure out that there's a constant you can add here. If we throw in an R, which we're going to use as our proportionality constant, we're going to throw in R here. It makes all of this become equal instead of just proportional to. So what we've made here is called the ideal gas law. If you look at your equation sheet, you have it written as PV equals nRT. That's exactly the same as what I have written here. I'm just bringing the V over to the other side so that it's all in one line. There's no fraction. But that's where we get that. So pressure and volume are indirectly proportional. If pressure goes up, volume has to go down if these things stay the same. If pressure goes up or temperature goes up, pressure goes up. So think about just looking at that relationship, this equation, and can you find those relationships we just talked about in this formula? So this is the ideal gas law. You're going to use this when you have one of each variable in the problem. Like you are asked for pressure, but you're given volume and moles and temperature. You're always given R. R is on your equation sheet 0.08206. It has units. These are the units of R. You don't plug numbers in for these units. These are just the units, not variables. So don't plug in numbers in place of those. Those are the units. So if you're going to use ideal gas law, you must have pressure in ATM, volume in liters, moles, N in moles, and T in Kelvin. You have to match the R units. There are other R values that you may encounter in your chemistry career, but we are just going to use this one. So even if you go online and you find others that make your problem math easier, just use the one I give you because I'm looking to see that you're checking your units. I'm wanting to test that. So don't just go find an easier R to make your homework easier because I'm not going to give you that on an exam. So this is the ideal gas law. If you find you have one of each thing in your problem, this is what you're going to use. Make sure you know how to algebraically rearrange to solve for all of these things. If you're having struggles with just rearranging algebra like this to solve for V or solve for T, for example, then come and see me and we can try to work out where you're getting lost in that. So next is the combined gas law. So what a combined gas law is talking about is we have some initial conditions and we're trying to compare them to final conditions. We have a scenario, has a certain pressure, has a certain volume, has a certain temperature, and we're going to change the pressure, change the volume, and find out what the new temperature is. So we have initial conditions and final conditions. Initial conditions are ones. Final conditions are twos. And let me explain where we're getting this formula from. When you do gas law work, because everything is proportional to each other, if we look at PV equals nRT, let's solve for R. R is equal to PV over NT. Now, that means that if I have a pressure and a volume and a moles, the temperature will have to be something that makes all of this be R. It's not that any pressure, any volume, any temperature, any moles can be put together and that will work out. It won't do it. So in an ideal gas situation, you'll learn more about real gases later that are less ideal. But in an ideal gas situation, these all will have to work out in this way to equal R. So imagine that these are initial conditions. So if I say, hey, here's my initial conditions of pressure, volume, moles, and temperature, they're also equal to the final conditions. The final conditions also equal R. So we can set them equal to each other. So initial conditions equal R, and R also equals final conditions. So we can just get rid of R, and we can say that initial conditions are going to overall equal the final conditions. But instead of writing all this initial and final, let's just use ones and twos. So we get our initial conditions where everything is labeled as a 1, and our final condition where everything is labeled as a 2. Come on, Cordero. Okay. So that's where it comes from. baked into the combined gas law are all the other gas laws that you may have heard of before, or you may see in textbooks and whatnot, or you may hear later in future classes. Charles's law, Boyle's law, Gay-Lussac's law, Avogadro's law. It's all built into the combined gas law. And what I'm using here is the super combined gas law. It's not really even the combined. The technical combined gas law doesn't have N in it, but I just like to say, you know what, let's just put them all there. Then what you can do is cross out or erase variables that are constant or that are not mentioned. So if the problem doesn't mention moles at all, that's because moles are not changing. Or if they say pressure is constant. So if your problem only needs pressure and volume, you just get rid of everything on the bottom down here and just write P1V1 equals P2V2 and work through that equation. A couple of notes here about units. Because we don't have R, we're not as limited to the units we can use. Pressure and volume units can be any unit as long as they are the same on both sides. For example, if your pressure is ATM for P1, your P2 is also ATM. If your V1 is milliliters, your V2 is milliliters. It just needs to work out so that it cancels out. And another note I would add here is cross multiply the variables before you plug in the units, or sorry, plug in your numbers. Because a lot of students get lost in solving for T2, for example, and if you were just to cross multiply first, then rearrange your variables before you plug in numbers, it'll make your life a lot easier. But I'm leaving off an important note here. All N units must be moles. Well, this is not changing. All T units must be Kelvin. So that is the combined gas law, and you're just going to use algebra, identify what you have in the problem. This is when you have initial and final. So they give you a pressure, ask you for a new pressure, give you a volume, then give you a new volume. You've got more than one of the variables. Ideal gas law, you just have one of each variable. Next, looking at Dalton's law of partial pressures. This one's really straightforward. He said the total pressure in a container is equal to the pressure of all the components added together. So if I have a container of oxygen and nitrogen and argon, the total pressure is going to be the pressure of the oxygen plus the pressure of the nitrogen plus the pressure of the argon. It's not really that complicated. Don't overthink it. If you have multiple gases inside of a container, you add all their pressures up, you're going to get a total pressure. And then lastly is the molar volume. So we have special conditions called standard temperature and pressure, STP. And I'll show you what that is in a second. 1 mole of gas is equal to 22.4 liters of gas. So this is a conversion factor we can use. Instead of doing the ideal gas law, we can just plug this in as a conversion factor. You can use the ideal gas law if you want to. STP is the temperature of 0 degrees C or 273.15 Kelvin, and pressure is 1 atm. I use 0 Celsius and 1 because in my head 0 and 1 is easier to remember. So if you remember what STP is, if I tell you, hey, this is at STP, you can use the ideal gas law and put that T in and put that P in, or you can just use this conversion factor and do quick dimensional analysis to go from moles of gas to liters of gas. This has to be gas. No other type of matter. This does not work on solids, liquids, anything else, only gas. And it has to be at that temperature and pressure, or that's not true. So that's pretty much all you need to know about gas laws for this class. You're going to go into a lot of more information on gas laws as you move farther along in chemistry. I will make a separate video where I go through and do some examples for these, but you should have enough information now to go ahead and give some homework a try.